Okay, so we're going to take a look at some more geometric sequences, and this time though they're going to have a real life context, and some of these are going to get particularly challenging as we go through. So let's read them very carefully. Okay, so first of all, we've got a population of rabbits, and we've got 50 of them, and it's increasing by 7% a week. Now, there's a problem here that I want to just explain to you before we go any further. So usually what we would say is U1 is equal to 50, and R is then equal to 1.07, and that makes a lot of sense to me. So, but the problem is this, is that after 1 week, right, we would have 50 multiplied by 1.07, and okay, so that's after 1 week, and then of course after 2 weeks, then we would have that times 1.07 squared. But the problem is that this week number doesn't correspond to the term number, because that would mean that this is U2 and this is U3, right? And the 2's and the 1's are not matching up. So I want to stop this and reset this problem in a bit of a better way. So for this sort of problem, there is a new formula that we can perhaps use and just adjust it to do with this week number. So what we're going to say this time is that we're going to have a U0 multiplied by R to the N is equal to U to the N. And I'm doing that so this issue with the week number doesn't affect us. So U0 is going to be like our initial amount, right? R is going to be like the growth multiplier. That's our common ratio, really, because we are still thinking about this in terms of geometric sequences. N is the number of time periods. Well, in this case, it's easy, isn't it? We are talking about weeks, and therefore this is the amount after N time periods. Okay, so if we reframe our problem a little bit like this, is going to help us to really understand and keep this easy. Right, okay, so in this case, using this terminology here, we've got U0 is equal to 50. We've still got R is equal to 1.07 for that increase of 7%. Okay, let's see if we can work this out. So in a part 1, we have N is equal to 15, and we can just think straight away, no problem at all, N is 15, no need to worry and make those adjustments. So our answer to this, how many are present? That's U15 is going to be 50 multiplied by 1.07 to the power of 15. Okay, so that comes out rounded to 137.95. So we'll have this to the nearest rabbit. We don't get 0.95 of a rabbit, so that's 138 rabbits. Now, in part 2, we have to do 30 weeks. So we're looking for U30. Well, that will be 50 multiplied by 1.07 to the 30. And if we work this out, it's going to come out at 380.61. And again, we need to round this to the nearest rabbit. So that is approximately 381 rabbits. All right, let's move on to part B. So how long is it going to take for this population to reach 500? Now, I'm going to talk through, but I won't give you a diagram exactly of how I would go about doing this question on the TI-84 calculator. So what we would do, we'd press the Y equals button, and we'd input a formula. So the first thing we'll do, press that button, and where it says Y1 equals, we're going to type 50 multiplied by 1.07 to the power of N. And remember, we're just going to use that variable button to get that N. Okay, it might be denoted as an X on your screen, but we know it means N. All right, underneath that, I'd like you to type in Y2 equals to 500, because what we're going to do is we're going to find the intersection, right, of where our general formula meets that 500. Now, if we work out that, okay, we're going to do on our GDC, we're going to have the intersection. We are going to find that it's 34.0. So we're looking at 34 weeks as our final answer. All right, so that's how I want you to do that. See if you get the same results that I did. Let's move on to the second question. All right, we'll just do this one, then we're going to stop. So the an animal, Araticus, is endangered. Since 2005, there's only been one colony remaining. And in 2005, that population of that colony was 555. Okay, so let's start writing some notes. That's telling us that U0, our starting point, is 555. We've got our common ratio. Now, if we're decreasing by 4.5, that's equivalent to multiplying something by 0.955. Okay, right. So part A, we are going to estimate that population in the year 2020. Now, we've got that initial setup at 2005. So if we are considering the number of time periods since 2005, well, it's nice and simple now. It's just going to be 15. And again, think of it this way. I want this to be really explicit. 2006 is like n equals 1. 2007 is like n equals 2. 2020, well, that will happen when we've got n is equal to 15, all right? Okay, it's not going to be any different at all, right? So now we know all that, we can pop it into the formula and work it out. So u of 15 is going to be 555 multiplied by 0.955 to the power of 15. If we work this out, it's going to be 278.19. So we'll say 278 people. Okay, so that's what we're going to expect that to be in the year 2020. Right, B. In what year do we expect that population to have declined to 50? Right, we're going to do this exactly the same as last time. We're going to press the y equals button, and we're going to input a formula on our calculator graphically. 555 times 0.955 to the power of n. We need to know when it's equal to 50. So underneath that, we're going to set another straight line at y equals 50, and we're going to find the intersection. So if we find that intersection, we're going to find it that n is approximately 52.27. So we'll say 52 years. Now, that is not the final answer, though, because we want to know the year, right? So that means that we're going to have to add 52 to the year 2005. So 2005 plus 52 is going to be the year 2057, and that is the year we expect that population to have declined to 50. Right, hopefully this video made a bit of sense, and you can now have a go at some of these real-life applications.